Number 15. So this one might look a little bit confusing because we're given two coefficients of friction here. So this has some concepts in it, how do we know which one to use? So let's go ahead and start by drawing a free body diagram. We've got a box here, we're trying to push it with some applied force of 15 newtons, I'll call it FA. There's going to be some kind of friction force. We don't know if it's static or kinetic because we don't know if the box is moving just yet. But we know we have a normal force and we have a weight going down. So the first thing is that in the y direction, we know we are in equilibrium there. So we know that in the y direction, we have sum of the forces in the y equals 0. So normal force minus the weight equals 0. So we know that the normal force equals the weight. So that's going to be helpful because we need to know what the normal force is when we calculate the friction force. So we don't know if we're moving or if we're at rest. So one thing we can do is we can solve for the maximum possible static friction force that we could have, which has been defined as μs times n. This is the maximum static friction force that you have, and so that you're on the verge of slipping, but you're still at rest. So in this case, since the normal force equals mg, we can say that the maximum possible static friction force to have to overcome to get the box moving, you have to overcome this amount of force. When you put in the static coefficient in here and your mass, which is 3 kilograms, and g, we're going to get 11.76 newtons. So this is the static friction force that must be overcome. A 15 Newton force is applied. So that means that the box is going to be moving because we've overcome the static friction force. So now we know that this is actually kinetic friction force. And luckily, the kinetic friction force is always defined by mu k times n, in this case, mu k times mg. So now we plug in the 0.3 for the mu k into here, and we're going to get 8.8 newtons. So when it's moving, we don't need as much force to keep it moving. The coefficient of kinetic friction is less than the coefficient of static friction. So if the problem had told us that we were at rest and what type of force do we need to get the object moving, then we would have to have something greater than this amount to get it moving. But we know that since we've applied a 15 Newton force, that we must be moving, and then we can go ahead and use the kinetic friction force. The last problem here, and I don't want to get into all of the little details here, but just set this up, because this is a longer problem. We've done ones very similar to it. The applet question where we're pushing a box up the incline is the same problem as this one. So we're just trying to set it up here. We're trying to pull up the slope, so we have an applied force up the slope, we have a normal force, we have a weight going straight down, and there is a friction force because we're given that coefficient of friction. So there's a kinetic friction force. So that's our free body diagram. So most important thing is being able to draw the x and y components of our only diagonal force there, Wy, Wx, make sure the directions, and it's accelerating. So it's going to be accelerating this way because that's the way we're pulling it. So what you need to get out of this problem is just setting it up, separating the x and the y. So fx equals max, and the sum of fy equals may. Look at your diagram and write down all the forces in the x direction. We have Fa, which again, that's this one right here. We have friction force opposing that motion. We have the x component of the weight, opposing that motion. That's all the forces in the x is going to be max, or you can just call it ma. In the y direction, we're in equilibrium. We're not jumping up and down the incline. So we have the normal force in the y minus the y component of the weight in the y is 0. So that's basically, and then just be able to put in what each thing is equal to. That's really all you have to be able to do as far as the test is concerned. Just plug in what everything is. The friction force is mu k times n. The x component of the weight is opposite that angle that's given, so it uses sine, mg sine. That's equal to ma. And then here we have the normal force minus mg cosine, because the y component is adjacent, is equal to 0. So that's really all you have to really worry about. As far as solving this problem, you would need to go ahead and solve for the normal force, which is mg cosine theta, and then you would have to plug that normal force into here, and then you would have to divide everything by m, and that would then allow you to solve for the acceleration. So the acceleration would be 250 minus mu k 0.2 times m, which is 50 times 9.8 times cosine of 16. That's the mu n term, minus 50 times 9.8 times sine of 16, and all of that had to be divided by the mass to get a by itself, and that should give you 0.412 meters per second squared.